Hello friends, welcome to Machine Tool Design. We are studying the first unit, that is regulation of speed and feed rates. So in our last class we have discussed what are the different types of progression in which the speeds can be arranged with the aim that the deviation from the ideal cutting speed should be the minimum. And we saw the four progressions as arithmetic, geometric, harmonic as well as logarithmic progressions. And we found that the logarithmic progression gives us the best characteristics as far as the issue of deviation from the ideal cutting speed goes. So the logarithmic progression gives the minimum deviation from ideal cutting speed. However, while choosing a progression to make a practical gearbox, the geometric progression is used very often. There are many reasons for this, and we'll be covering these in detail. The first one is constant loss of economic cutting speed in the whole RPM range. Now, one of the most important things in industry is repeatability. You want to make a product, it has to be repeatable no matter at which RPM range this product is produced. So it is desired that even if there is any deviation from ideal cutting speed, that deviation should be remaining constant no matter which speed range you choose. You may be machining in a lower speed range or you may be machining in a higher speed range, but despite these variations, that deviation should be constant. So that is one of the requirements in the industry, so that the repeatability of the product, the kind of characteristics, surface topography the product produces, it remains unaltered. So let us try to see how geometric progression satisfies this kind of a condition. So let us come to our slide. Suppose the spindle RPM values constitute the following series, that is N1, N2, N3, Nj and Nj plus 1. So these are the different types of the number of speed steps that we have seen in the earlier analysis. In our earlier analysis we had 12 steps, so Nj plus 1 would be N12. Now consider that the optimum cutting speed V optimum, which is right here, is such that it lies between a certain number of speed Nj and Nj plus 1. So we see that between Nj and Nj plus 1 your V optimum will lie. So this equation will be pi dnj by 1000, which is the cutting speed obtained at RPM Nj. And then we have the next speed step, that is Nj plus 1, and the corresponding cutting speed is pi dn suffix j plus 1 by 1000. So your V optimum should lie between these two speeds. Okay, suppose it does lie between these two speeds. The next thing we have to see is what is the difference between the actual cutting speed and the optimum cutting speed. Okay, so let's say if the optimum cutting speed is here, and the pi d into nj by 1000 is the actual cutting speed. So what will be the difference? It will be obviously V optimum minus the speed at which you are actually machining. So that will be the difference. Okay, and this is called as loss of economic cutting speed. Okay, this is called loss. Understand, in stepped regulation, we must understand that in stepped regulation it is never possible to have the exact ideal cutting speed. We have to have a certain amount of deviation, because we really can't afford to have those very costly stepless drives. So but what we have to try is that deviation should be minimum. So coming back here, the loss of economic cutting speed has to remain constant. That is the main thing that we are looking for. So the difference between the actual cutting speed V optimum and the loss of economic cutting speed is maximum when the optimum cutting speed lies in the middle of the two speeds. Okay, so suppose your V optimum is exactly in the center. By exactly in the center, I mean to say that on the left hand side we have the lower cutting speed, and on the right hand side we have the higher cutting speed, and V optimum is exactly in the center. So obviously what will be the value of this? You have to simply average it out. So it will be pi d by 1000 nj plus nj plus 1 by 2. Okay, so this will be the speed in case your v optimum lies exactly in the center between these two speeds. Now let us take another case that the economic cutting speed, the deviation is maximum, and this is given by this delta Vj max. So the maximum cutting speed, the difference between the cutting speed and ideal speed will happen if your V optimum either tends to pi d nj by 1000 or it tends to pi d nj plus 1 by 1000. That means the V optimum is towards one of these extreme ends. And suppose, let's say, V optimum is tending to this while you're actually machining at this. So the difference between these two speeds will obviously be the maximum difference, the maximum loss of the economical cutting speed, and obviously that is given by delta Vj max is equal to pi d by 1000, and here this time it will be the difference, nj plus 1 minus nj by 2. Okay, so now we have got these two definitions. The first case, we have the V optimum is in the center, and in the second case we have said that this V optimum is at one of the ends. Okay, then here we have a simple substitution. We substitute the value of pi d by 1000 from this equation 2.2, and what this helps us do is bring in this V optimum right here. Okay, so your equation therefore becomes delta Vj max is equal to nj plus 1 minus nj by nj plus 1 plus nj times your V optimum. Okay, now you must be wondering why we have expressed this in this term. When we make this substitution, we get our V optimum speed, which is a constant speed, which really does not change, and the second is we express this entire equation only in RPM, that is nj plus 1 minus nj by nj plus 1 plus nj. Okay, now let us see the final step. Now what is this nj plus 1 by nj? It is equal to nothing but phi j. Okay, and the phi j is nothing but the geometric progression ratio, and then therefore we get Vj max is phi j minus 1 upon phi j plus 1 multiplied by your V optimum. Okay, now for a geometric progression, we have seen all different types of progression, but for a geometric progression we know that this phi value is always constant. That is the nature of a geometric progression. So no matter which speed range you're working in, your delta Vj max or the deviation, maximum deviation of your cutting speed from the ideal speed will always remain constant, and this will be a function of this expression, that is phi j minus 1 by phi j plus 1 times V optimum. So this is how we have obtained this. Now I would just like to elaborate this a little further. So now we have these 4 different progressions, and here you can see this is n1 to n12 given by the arithmetic progression, and here we see the column of phi. So this column of phi we see in all these different progressions. So here we see that the value of phi changes for each speed steps when it is the case of arithmetic or harmonic or even logarithmic. Okay, the only place in which it is actually constant is in the geometric progression. Okay, because that's the nature of geometric progression. That means n2 is phi times n1 and n3 is phi times n2. So that is the way the geometric progression is designed. So this is how we will see that because we have a constant phi in geometric progression, we can get a constant loss of economic cutting speed over the entire speed range. Thank you.